Sorry. Okay, so this is section 1.8, linear transformations. Okay, so what is a linear transformation? A transformation is linear if it satisfies two conditions. The first condition is sort of the freshman's dream. If you take u plus v and apply the linear transformation t, that's equal to t of u plus t of v, right? So you're allowed to break it up over the addition. And the second condition is that we can pull scalars out. So t of cu equals c t of u. Equivalently, we can check both conditions at once by looking to see if t of cu plus dv is equal to c t of u plus d t of v. Okay, so this last condition takes care of both a and b at once, right? So that's the definition of a linear transformation. Let's look at some examples. Let's let a be the vector given, and let's define the transformation t of v equal to a dot v, where a and v are both vectors in R3. So this is a transformation from R3 to R1, and this is linear. So let's look at t of u plus v. Well, that's a dot u plus v, but I'm allowed to break the dot product up over addition. So t of u is t of u plus t of v is equal to t of u plus v. The second condition I want to check is if t of cu equals c t of u. So t of cu is a dot cu, which again I'm allowed to pull the constant out by properties of dot products. So that's c of t of u, c times t of u. All right, so the conditions hold, so it is a linear transformation. Consider the transformation from R3 to R1 defined by t of v equals the magnitude or the norm of the vector v. This is not linear, so the magnitude of v plus w is not always equal to the magnitude of v plus the magnitude of w. This is the triangle inequality. So we have a less than or equal to sign here, but not always equality. Okay, so this is not true for all u, v, and w. So the first condition fails, and if c is negative, the second condition also fails. All right, so this is definitely not a linear transformation. Let's look at another example. Let t be the transformation from R2 to R2 defined by rotation by 45 degrees. Okay, so a point PQ, a vector PQ is rotated 45 degrees. Does this define a linear transformation? Now in the next section we're going to talk about how to write down a formula for this transformation, but for now I just want you to think about what's happening pictorially. Okay, so I'm going to draw some pictures. So here's a vector v and a vector u, and I want to take v plus u, so here's v plus u. Now let's apply the transformation. If I apply the transformation to v, I get this vector here. That's t of v. And if I apply it to u, I'm going to apply it to u and then move it on the end of v so that I can get t of u plus t of v. Okay, so that's approximately, if I rotate u 45 degrees and then move it on top of v, that's what I get. And so here's t of u plus v, but notice that that's the same as t of u plus t of v. The angle down here is 45 degrees. So we have t of u plus t of v is equal to t of u plus v. All right, what about our second condition? So here's my vector v, and let's take a scalar multiple of v. Here I'm assuming c is positive and greater than 1, but here's v and c of v, and now let's think about what happens when I apply my transformation t. So v gets rotated 45 degrees, and so does c of v. But that's exactly the same as C times T of V. If I were to extend T of V out by a factor of C, this is the vector I get. So again, the second condition is satisfied, and so T is a linear transformation. In the next section, we're going to talk about how we would actually write down formula for this. All right.